stationary and independent increments. Definition. So, as a matter of notation, let me just develop one notation right now. So, NT we know, right. So, NT is a counting process, the counting process NT is given. Okay. Now, I want to call n tilde T1 comma T2 as n of T1 n of T2 minus n of T1 for T2 greater than T1. Okay. So, this is just the number of arrivals in T1 T2. Okay. Just notation n tilde T1 T2 is the number of arrivals that occurred in the interval T1 comma T2, T1 not included, T2 included. Okay. Just a convention. Now, definition: a counting process NT is said to have stationary increments if n tilde T comma T prime has the same distribution as n of 0 comma T prime minus T for every T prime greater than T greater than 0, be true for every. Okay. Every is important. So, this is a property called stationary increment property, or for short SIP. Okay. Stationary increment property. So, we say that the counting process n of t has stationary increments if the number of arrivals in any time interval, let us say t comma t prime, the number of intervals has the number of arrivals in that interval has the same distribution as the number of arrivals in 0 to t prime minus t. Okay. In other words, the distribution of the number of arrivals in any interval depends only on how long the interval is, right. So, if you look at, so if this is your time axis, right, this is 0, let us say that is t, that is t prime, okay, and you have some arrivals, all right. You just look at the number of arrivals in this interval t comma t prime, and you look at another interval of the same width, but starting at the origin, right. Say this guy is okay. So, you take these two random variables, right, n. So, the number of arrivals that occurred in t comma t prime, number of arrivals that occur in 0 comma t prime minus t. So, you are considering two intervals of the same width, one is located at the origin, one is located anywhere else. Okay. If the distribution of the number of arrivals is the same for any t prime and t, then you say that the process has stationary increments. Okay. So, what I really mean is, yeah, thanks for pointing out. I should be saying, I should, let me just erase this. I should really be saying n of t prime minus t, right, or I should say n tilde of 0 comma t prime minus t, which is the same as n of t prime minus t, right. So, it does not matter where the interval is located, the number of arrivals that occurs in an interval is only it only depends on the width of the interval and not where the interval is located, right. This interval could be at the origin or anywhere else, as long as the width is fixed, the distribution of the number of arrivals in that interval is fixed. Okay. I mean, it is not, I am not saying that this is always true, I am saying that if this is true, then such a process is said to have stationary increment property. Okay. Is that clear? And we will define independent increments also. Definition: a counting process n of t is said to have independent increments if for any integer k greater than 0 and times 0 less than t 1 less than t 2 less than t k, the random variables n of t 1, n tilde t 2 comma t 1, or I should say t 1 comma t 2, I think, sorry, the smaller time always first, so until n tilde t k minus 1 t k are independent. Okay. So, you are looking at, just go back to this picture again. So, that is 0 and you are looking at times t 1, t 2, t 3 dot 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 t k minus 1 t k. Okay. So, this you can choose any k you want and any t k's. Okay. You choose them whichever way you want, but they are fixed. Okay. And then you look at then of course, the process is running, right, the counting process is running. Then you look at n of t 1, n tilde of t 1 comma t 2, basically you are looking at the number of arrivals that occur in each of these intervals. Okay. So, this will be some random variable, this will be some random variable and so on. So, you get how many random variables now? K or k, right, you get k random variables, there is n of t 1, n of t, n tilde t 1 t 2 and so on. These k random variables should be independent. Okay. No matter how you choose the t's. Okay. You can choose any number of k can be anything and t 1 t 2 3 t k can be anything. for every such k and T1 T2 Tk, if this k tuple of random variables are independent, then the process is said to have independent increment property, okay, IIP for short. Okay. K random variables being independent, you know what it means, right. The joint CDF will factorize into product of the marginals, right. This should be true for every k and every T1 T2 Tk. Okay. If it is not true even for one such tuple, then you know one such selection of the times, then the process does not have IIP. Okay. So, we have just defined two properties, okay. One is the stationary increment property, one is the independent increment property. Okay. It is of course not at all the case that a counting process should have either of these, okay. It could have one or not the other or neither. Okay. Now, what we are going to say next is that the Poisson process has both properties. Okay. The Poisson process has stationary increments and independent increments. Poisson process has stationary and independent increments. So, this theorem is actually a consequence of the the memoryless property that we proved in the previous. So, you remember this theorem, right. So, it is a consequence of both IIP and SIP are consequences of this theorem. Okay. So, in particular, if you want to look at the stationary increment property, you are starting at some time t and looking at, let us say, the number of arrivals that occur from t to t prime. Okay. But we just proved in the theorem that the process restarts at t, right. It forgets everything that happened in the past. It is as though the Poisson process is starting at the t. So, that t sort of behaves like 0, right. So, the number of arrivals that occur in the time t to t prime will be the same as the number of arrivals statistically distribution wise, the same as the number of arrivals that occur in 0 to t prime minus t. Okay. So, this can be formalized using the theorem that we proved earlier. Okay. Clear? So, stationary increments is a direct consequence of this theorem. Independent increments is also a consequence of this theorem. It requires a little more argument. Okay. So, in fact, if you look at this argument, I mentioned that so if you are here at t and if you are looking at the number of arrivals in t comma some t prime, right, we want to prove that that is independent of the any if you mark t1 t2 etcetera here, right, that so basically you can argue that, so you have shown that this z, the time to the next subsequent arrival, is independent of all the NTs here, right. So, you have proven in this, essentially in this argument, that z is independent of n of t1, n of t2, n tilde t1 t2 whatever, right. You mark those times here. You just have to prove that the number of arrivals in t to t prime, any t prime that you mark out here, is independent of the arrivals that have come so far. That will come from the property of z being independent of everything in the past, and the subsequent arrivals are anyway independent of everything that happened in the past, right. So, you can put these two together and make this formal. Actually, your book, Gallagher's book, has this argument written out, but this is all there is nothing more to it than just in this theorem. It is just a consequence of what we proved. Okay. So, you will get this very important result, right. A Poisson process has stationary and independent increments. So, what that means is that if I take a Poisson process, so you have some Poisson process running. So, because of the stationary increment property, if you take any interval like so, the number of, so let us say this is t 1, this is t 2. So, the number of arrivals in an interval like this will only depend on the width of the interval, it does not matter where the interval is located. Okay. It will depend only on t 2 minus t 1, it will not depend on the actual values of t 1 and t 2, correct. So, this interval might have been here or it does not matter where it is, that is what stationary increment is saying. And the independent increments is saying that if you consider many intervals like that which are non overlapping, basically there is, if the intervals are disjoint, then the random variables corresponding to the number of arrivals in those intervals will be independent. So, all I am saying is that, see, you have taken, so let us say this is t 1, okay, so let me say, so this is t 1, t 2, t 3, t 4, whatever, right. So, the number of arrivals in this interval, which is n tilde t 1 t 2, is independent of number of arrivals in n tilde t 2 t 3 or t 3 t 4, any non overlapping intervals. If you look at the number of arrivals here and the number of arrivals here, they will be independent random variables for any non overlapping intervals. It does not matter how big it is, it does not matter where it is, as long as they are not overlapping. The random variables will be independent, and if the length of two intervals are the same, then the distribution of the number of arrivals will be the same according to SIP, stationary increment property. Okay. So, SIP says the number of arrivals in any interval depends only on how big that interval is and not where that interval is located. Independent increment property says that if there are non overlapping intervals of time, they do not have to be of the same length, they can be of different lengths. If they are non overlapping, the number of arrivals in this interval and number of arrivals in this interval are independent, okay, they are independent random variables. Is that clear? They are not the same thing, right, they are two very different properties. It just so happens that the Poisson process has both the properties, okay.